A really revealing and interesting thing to do is to move just a regular ordinary wire through a magnetic field. That magnetic field does something to the charges in the wire, and we can detect what it does with a sensitive voltmeter. Here we have a normal magnet, and there is the magnetic field coming from the north to the south. Here we have a normal wire plugged into this very sensitive micro voltmeter. And what we can see is as we move the wire, we're getting absolutely nothing happen at all in that direction. But watch what happens if we move it this way. What you can see is we're getting a deflection of the needle. It's quite slight because this magnet isn't very strong. But notice the difference. When I go this way, in line with those field lines, there's almost no deflection on the voltmeter. But when I cut across lots of field lines, I get a much stronger deflection. So I wonder if we could see this with a much stronger magnet. So look here. What I've done is I've placed two magnets on the ground. The north pole of this magnet is closer to the south pole of this magnet than it is to its own south pole. So the magnetic field lines actually form straight lines straight to the nearest south pole. This has created a uniform field. Watch what happens as I move across the field in the same direction as the field lines. There is very little deflection of the needle. But if instead I cut through the field lines, at right angles, you can see I'm getting a significantly larger deflection. Now, that is also true with the ends of a horseshoe magnet. This horseshoe magnet has very, very little deflection if I do it in line with the field, but if I cut through the field at right angles, the deflection is off the chart. So what does this mean? It means when my wire cuts through those field lines, it induces a potential difference in this wire that this voltmeter can detect. Now, a single wire and a magnet are going to create a really minimal and hard to detect effect. So one thing we can do to amplify the effect is turn that wire again and again and again into a coil. A solenoid like this. Now this becomes so sensitive to magnetic fields that me moving this magnet right over here is having an effect. I'll move it out of the way. Now, what I find now is that it's so sensitive, I need to turn the sensitivity right down on my voltmeter so that we can actually see the effect. There we go. And what do we notice? Well, to start with, if I push my magnetic field in, then you can see that the voltage is deflecting in a negative direction. Pushing it in creates a negative voltage. And that is because the electrons are trying to oppose the change that I'm introducing. I can't push and find that they, go the other way. It's not how friction works. And if I push in, there is this opposition to the change I'm trying to make. So there we go, you can see that it deflects. If I change the polarity of the thing, it tries to go the other way. Watch what happens if I do it quicker. Oh, I missed it. If I do it quicker, I actually get more deflection. And so this reveals to us how we get a strong signal here on this voltmeter. More turns on the coil will give a greater potential, but also moving my magnet through it would give a greater potential if it's faster. This is because we're cutting more field lines per second, and that is the key thing. The more rapidly I cut through those field lines, the greater the detected voltage. And this gives rise to some really interesting effects. Alright, check out this apparatus here. I've got a coil and I've got a magnet. I'm going to drop the magnet right through the middle. And I want to see what happens on this detector, which is going to record the voltage as a function of time. So I'm going to press play and I'm going to drop the Magnet 3, 2, 1. There we go. Look at that. There was an initial quite small positive voltage induced in the coil, and then a much larger negative voltage induced in the coil. Now, what that was caused by was, if you think about this magnet first starts to push as the north pole approaches the coil, but then as the south pole exits, it starts to pull. And so the difference in direction between the north and the south pole creates the positive, then the negative signal on there. So why is it that the negative signal is larger than the positive signal? It's because it's moving faster because of its acceleration due to gravity. It actually exits the coil much faster than it enters. And so we see a larger response when it exits the coil. Generating an induced potential difference, a voltage, is great. But if we complete the circuit, and in this case we've taken each of these coils and completed the circuit by putting an LED in it, and it's not just a voltage that you're going to induce. The movement of these magnetic field lines past these coils is not only going to push on the electrons, because they are now circuits, it's going to enable them to flow as a current. And what we can see when a current flows is that these LEDs will light up. As the magnet goes through them, it causes these LEDs, in turn, to illuminate. Let's see that in the dark. Woo-hoo-hoo. I am the Darth Vader of physics. Another really exciting application of this is in the railgun, and I've got like a simplified model of it here, sometimes called the jumping ring. What I've got is a coil of wire here, and I'm going to pass an alternating current through this. So it's not a constant one-way flow, it's alternating backwards and forwards. Now what that alternating current does through this coil is it sets up one moment a positive magnetic field, and then the other moment a negative magnetic field, and then the other moment a positive magnetic field, and that continual change in magnetic field induces a ginormous current around this ring called an eddy current. Now that eddy current swirling around the ring will actually make this turn into a magnet. The magnetism induced in this will push against the electromagnetism in that and should hopefully push two north poles away from each other. Let's give it a go. Whee! It's magic! Let's do it again, but harder. Look what happens. I've cut the ring. I've made a little cut in it. And all that will do is mean that rather than an eddy current flowing around this, there'd be a potential applied around the ring, but no current could flow because there's a break in it. Now, if everything we've said is true, then what we should notice the difference is that would not, therefore, enable this to become a magnet. There'd be no magnetism induced in this second ring, and therefore nothing to push against the electromagnetism of that coil. How sad. It doesn't do anything. But it's proof that electromagnetic induction can turn this just plain ordinary ring into a magnet and push it away from that electromagnet. Proof of electromagnetic induction.